Now we're going to discuss how you can take experimental data and figure out the rate law for a reaction. So these rate laws are really important if you want to describe the kinetics or be able to predict how fast a reaction will go, because you want to control how fast a reaction goes. You need a rate law, which means you need to know the rate constant, the value for it, and the order of each reactant. What is the value of the order of each reactant? So this is kind of a broad overview of how you go through it. We're going to work an example, but generally what you do is you use what's called the actual experiments are the initial rate method. And so what you do in the initial rate method is you measure the rate of the reaction under a different set of initial reaction concentrations, reactant concentrations. So you basically, if you think about the purpose of orders, it was the idea of like, well, if something is first order, when you double that concentration, you double the rate. And so the idea is we're going to literally do that. We're going to do experiments where we have the concentration of a reactant, we double it, do a second experiment, and then see the rate and see how the rate changes. So we're going to do that in a strategic way to determine the rate for each reactant. And then we can put that together to figure out the rates for everything and figure out K. So let's look at an example. I got the reaction of H2O plus CH3Cl. That becomes CH3OH plus HCl. So we're going to do this reaction, and we run the reaction multiple times. And what we do is we set up some initial concentrations. So we set up initial concentration of water and initial concentration of the CH3Cl, and then we measure the initial rate for those different trials. And the idea is the reason why we measure the initial rate and not like a rate over time is we want to know what the rate was for those actual concentrations that we were looking at, right? The actual concentrations that we set up, that we'd specified for our reaction. Because that's really what will help us figure out the actual rate law, right? That gives us an apples to apples comparison of the concentrations and then the rates. Basically, you set it up, you start the reaction, you see exactly how fast it is, and then you set up a new one. So if I want to determine the rate law here, I know that when it comes to determining the rate law, what I need is the rate constant and then an order for every single reactant. So if I have all that information, that would mean I know the rate law, right? Because everything else is the variables we'd want to use experimentally. The reactant concentrations and the rate we actually would calculate. So you start always by determining orders. We take a look at, used trials where the only difference is the concentration of one of your reactants. So if you look at, for example, trial 1 to trial 2, the CH3Cl concentration stays the same, while the change in the water concentration, there is a change in water concentration, which means the change in the rate is due to the change in the concentration of H2O, right? We can explicitly figure out that is what caused it, right? That is explicitly what drove that effect or caused that change, was the actual change of the water concentration. So we can figure out the order for just that compound. We'll divide it out. We'll go through that process. I'll write it out. We would do that for every single reactant. So we do it for H2O, we do it for CH3Cl. We pick the trials that were designed to serve to isolate out the effects of each individual substance. That tells us the order for each of those. And then we can plug those all of our obtained orders for a single trial to solve for the value of K. We also get the units of K. Don't forget that, which comes from the total order. So let's see what that looks like.
All right, so we've got this initial rate data, and what we want to do is figure out the rate law for this chemical reaction. And so if we want to do this, we can when we want a rate law, what that means is we want to be able to write this equation where rate is equal to K times the concentration of each reactant, so my concentration of water, times my concentration of CH3Cl, and each of those is going to be raised to an exponent. So really, I need three things. For this case, three things. I need two things in a general sense. I always need the rate constant. and then I need the order for each of my reactants. So in general, orders and rate constants. And so what I'm going to do then is basically take it one at a time and see if I can get that. I'm always going to start with the orders. So if you figure out the orders, you can then from that figure out the rate constant from there. So we're going to try to figure out the orders. So you'll note we have set up multiple trials. When you're doing initial rate experiments like this, you always have to do more than one trial. And basically what we did is we mixed water, reactant 1, CH3Cl, reactant 2, at given concentrations, and then you measure the initial rate. So for these concentrations, what is the rate? What that lets us do then is we can say, well, for trial 1, I would have my rate, and I can know what it is. So I can say like, well, trial 1, I can plug in my numbers. I know that my rate was the 0.015 molar per second, and that's equal to some K that I don't know, times the concentration of water, 0.05 molar raised to some power X, which I don't know, times 0.05 molar concentration of this raised to some power Y. So I don't know what the K, X, and Y are, but importantly, because of how I did the experiment, I know all of the other numbers. What I also know is that for trial 2, I have that the rate is 0.060 molar per second is equal to the same K. As long as my temperature stays constant, K is just a number. In this case, 0.10 molar raised to the same power X, and then 0.05 molar raised to the same power Y. So I can set up these equations like this. And so what I'm going to do, what I can do, is I can take trial 2 and divide that by trial 1. And what that will look like is I take the left-hand side, so trial 2 is 0.060 molar per second, divided by 0.015 molar per second, is equal to, I just take the whole thing, K times the concentration of 1.0 molar to the X, times 0.05 molar to the Y, divided by the whole thing for trial 1, 5 molar to the X, 0.05 molar to the Y. And the reason why I set it up like this is we can see there's a decent number of things that are going to cancel out. Namely, those K's are the same. This whole 0.05 molar to the Y, 0.05 molar to the Y. I don't know what those Y's are, but the 0.05 molar to the Y equals a constant value. And so you'll note this is these cancellations were intended when I set up the reactions in this way. You can see the only thing that's left is this concentration of water. And if you look at these reactants, you can see the concentration of water increased, but the concentration of CH3Cl did not change. So what that tells me is that between these two rates, these two measured rates, the difference is entirely based upon the change in concentration of this one reactant. The whole purpose of order, or the whole idea of what order, reaction order describes, is the effect of changing the concentration of this one reactant on the overall order. So by designing our reactions in this way, we're going to be able to isolate out the effect of just this one reactant. So, so if we look mathematically, we can kind of see, what's going on here. Is I can simplify these units also cancel out, worth noting. The units all cancel out, boop, boop, molar per second, and 0.060 divided by 0.0150 is 4.0. Here I have a value raised to an exponent, a different value raised to the exponent. So if I write it out, 0.01 molar to the X divided by 0.05 molar to the X, because they're raised to the same exponent, I can rewrite this to be 4.0 is equal to everything raised to that exponent, the single exponent, right? I can pull it out, similar to distributing, all raised to the power of x. Those molarities cancel, and I get 4.0 is equal to 2 to the x. And so this was all intended with how I set up my reactions, that I chose my reactants that basically the K's always cancel. The other reactant, that order cancels out. The only variable I have left is the order of the reactant I changed. And I can see that 2 to some power, which is the order, gives me the effect on the rate. You may be able to do this kind of looking at it, but we're going to go through, you can use logarithms. The tool to solve for variables that are in exponents is always logarithms. So I might as well move it to the second page. So I have 4 is equal to 2 to the x. I take the log of both sides. When I take a logarithm of a value that is raised to an exponent, so log of 2 to the x, I can take that x, bring it out front, and this becomes log of 4 is equal to x times logarithm of 2. Logarithm is just a process that takes a number and gives you a different number. So logarithm of 4 is a number, the logarithm of 2 is a number, and I can get that x is equal to the logarithm of 4 divided by the logarithm of 2. You compute that, you get 2. You may have been able to know 2 to what power gives you 4, right? That's the question that logarithms answer. This number, or, a number raised to what power gives you a different number. That's why we use logarithms here. And so to remove the exponents, that's the job of logarithms. And so when we're working through this, we can always get this result. Now, you may have been able to do it in your head, but you certainly don't need to. And there are some cases that you can find where you couldn't get everything set up perfectly to have so many round numbers. And so you do need to use the logarithms because you're taking 2.5 raised to what power gives you something else. It's harder to do those in your head. So what does this mean? X equals 2. Well, if we return to our original expression, X was the power on water. So what this tells us is that H2O is second order. Which is good to know. If we return to our original reaction, original results, we can see where this comes from. If we look between trial 1 and trial 2, these two values are the same, right? So because those are the same, that means that is not affecting the rate. Any change in rate is not based off the change in the concentration of CH3Cl. It's contributing to the rate overall, but it's not contributing to this change. And this change, 0.05 to 0.06, is times 4. Whereas this change right here is times 2. So what we can see is that you doubled the rate, the concentration of water, that caused the rate to quadruple. So really, all of this math right here gets you to this question of you doubled the rate. So you doubled the rate, or doubled the concentration, sorry. You doubled the concentration and you observed a times 4 effect on the rate. So what power gives you that? Okay, so you can work through all of this math right here to get that expression. And sometimes the changes aren't so clean, but you can also just analyze the data right here and come straight to this relationship. That because this was times 4 and this was times 2, we can do that. Now you don't have to jump straight there. You can always work through this. This will always work. I like doing this. I like using this method. It will always work. But you can always, if you kind of can see it, you can jump through. And the more kind of comfort you gain with this, you can kind of work through those things. So that gives us the order for X. We still need the order of Y for CH3Cl, and we still need to know K. And in order to get K, we need to get that other order. And so this is where trial 3 comes in. You'll note with trial 3, these are now the same, which means that you didn't affect that concentration at all, but you did change this concentration, and the rate does change. So what we can see then is by going from trial 1 to trial 3, with trial 1 to trial 2, we were looking at just changing the water. Trial 1 to trial 3, we're only changing the CH3Cl, seeing how that's going to be affected. And so we can go through and set ourselves up. We're going to do trial 3 divided by trial 1. And so I'm going to take my rates. Doing the same idea I did with trial 2 divided by trial 1. I'm just doing trial 3 now. We're at 0.05, 0.015. Again, I get the K times 0.05 molar. I can put squared here because that's my concentration of water, and I know what the concentration or the order on water is. Sometimes you need to use that if that wasn't held constant, but because it's held constant, it's just going to cancel out here. Right, we can put that squared in both places. Oh, whoopsies, there's no 0 there. Sorry about that. And it's just 0.15 and then 0.05. So for cancellations, K, that whole thing, molarity per second. If we divide those out, I get 3.0. And then over here, I can work similarly, and I end up with 0.15 molar divided by 0.05 molar to the Y power. We know those molarities cancel out. Three is equal to 3 times what power? 3 to what power, not times what power, to what power. And if I want, I can do my logarithm. You may be able to see this one. I get that the log of 3 is equal to the log of 3y. And then I get that the log of 3 is equal to y times the log of 3, which eventually tells me that y logarithm of 3 divided by logarithm of 3. I don't even, those are just, that's logarithm to a number, that's a process to a number, process to number, those have to be the same. Y is 1. It tells me that CH3Cl is first order. First order, we can go back to our initial data. We can see that we changed the concentration here, 0.05 to 0.15 is times 3. 0.015 to 0.045 is also times 3. So we can see with the second order, it was 2 to the second power gave me 4. 3 to the first power gives me 3 because this is first order. So we can figure those out, figure out our order. All right, final step, solve for K. So we know a lot now. We know we have our rate. Our rate is equal to K times the concentration of H2O to the second power times the concentration of CH3Cl. It'd be to the first power, but we just don't write that there. So what this means is the only variable I want to know is K. I have an equation. If I know every other variable, I'll be good. So what I can do is I just pick any of the trials, because that gives me concentration of reactant, and rate. And I can just plug those values in. I know the orders, so those are already plugged into the expression. I'm just going to do trial 1. You can do whatever you want. Because I made up these values, they work. Any of the trials work. A lot of times what you would do is plug in all 3 of the trials, solve for K, and then average. So K is going to be equal to 0.015 molarity per second divided by 0.05 molar squared, 0.05 molar. Some units, one of those molarities is going to cancel out. And what we are going to be left with, if we do it numerically, is I think we get 120. And then it would be 1 over molar squared is still there, times seconds. So overall, our rate law, rate is equal to 120 times the concentration of water squared times the concentration of methyl chloride, sorry. CH3Cl, doesn't matter what the name is. And so you'll note, now that we have K and now that we have the orders, we can have our full expression. Where if we want this, if we plug in these numbers, we can figure out the rate. If we have a target rate, we can plug in those concentrations, we would have everything. So it's a bit of an involved process, but this is a very, very useful reaction. We know we can pull out things. If you really want to change the rate, if you want to make it faster, if you want to make it slower, you're going to get more bang for your buck if you control water, right? If you change the water concentration, if you want to make it faster, put in more water. That's going to square the effect. If you really want to slow it down, you can also decrease the amount of water. That will really slow your reaction down. Changing the CH3Cl will affect the rate, but not as much. If you have to spend money, say, putting in extra water or taking out water or something to affect your rate, you're going to get more effect. It's going to be more effective if you move whatever has the second order, right? That's going to let you kind of be able to have more control and bigger effect on the reaction order. So it's a lot, but it's quite useful. And it is overall going to be this process of working through. You don't necessarily have to do as much work with all the logarithms and stuff, but you certainly can, and you can work through those ideas and get a very useful relationship.
Participation 911, question 3. Determine the rate law for the following reaction based on the given initial rate data. 2NH3 becomes N2 and 3H2, and then the data is given right here. This is the third question on participation 911, due Friday, September 11th at 11:59 p.m. over on Blackboard. The link to the assignment is right below the document where these videos are posted. Again, determine the rate law for the following reaction, this one, based on the given initial rate data in this table down here. Okay, we had 3 questions for our participation assignment due Friday night. You want to find all 3 of those questions, get them answered, and get the answers submitted over on Blackboard by Friday night. Answers to that will go live Friday. That'll be the end of any sort of material this week. I hope you're enjoying the start of chapter 12. And then Saturday, we'll have the week 3 homework and the post lab for the heat of fusion of water. That's not kinetics. So if you're not liking kinetics, do the post lab. If you have any questions about anything, let me know. Otherwise, have a good weekend. I'll see you around. Bye-bye.